right, so we're now talking about we're still in chapter 4. We're going to talk about internal symmetries now. So just as a recap, we went over, so we started off chapter 4 talking about the Lagrangian formalism, and we talked about how we usually start with a Lagrangian. We start off by proposing some sort of Lagrangian, and from the Lagrangian, we feed it into the Euler-Lagrange equations, or the Euler-Lagrange equation, and then from the Euler-Lagrange equation, we get our equations of motion. And I'll add, I'll move this over a little bit, and I'll erase this arrow, because between going from the Lagrangian and the Euler-Lagrange to the Euler-Lagrange equations, we talked about the principle of least action, right? And so, and fundamentally, what the Lagrangian was a function of the positions and the momenta, or the velocities, of all the independently moving parts within a system. So we were able to start off by saying, say you had like a Atwood machine or something like that, and associated with that Atwood machine is a Lagrangian, and we can derive all the equations of motion that Atwood machine abides by, simply by stating the principle of least action and deriving the Euler-Lagrange equations from that of motion. So this would be stuff like F equals ma, the Klein-Gordon equation, the Dirac equation, Broca equation. You could in theory find a Lagrangian that would lead perhaps to your Schrodinger equation, or you could find a Lagrangian that would lead to some arbitrary equation of motion, just some arbitrary differential equation, which is what all of these things are. So, and you could, so from a bird's eye point of view, and I've thought about this, a Lagrangian, you can go through all of these steps, right? You can go through all of these steps to get a differential equation. Because the equations of motion are really just differential equations. So we could generalize this if we wanted to. So we went there, and then we talked about symmetries, right? So we talked about what would happen to these Lagrangians if we shifted our perspective in terms of space, or if we shifted the time. What would be the invariant things that would come out of that? Well, we said if we shifted space, or if we shifted in space, then and nothing changed in our Lagrangian, then we said there would be momentum conservation. If we rotated our space, then the thing that wouldn't change, if the Lagrangian didn't change, we would have angular momentum preservation or conservation. And if we shifted our time, then the claim was that we would have energy conservation as described by our Lagrangian. And we were able to show, using space-time shifting, that the Lagrangian was resulted, or the thing that didn't change in the Lagrangian was the energy momentum tensor. And so, my apologies, my dogs are being a little bit weird. Okay, they're settling down. the thing that didn't change again was the Euler, or was the, what was I lost my train of thought. Anyways, we applied, or the thing that didn't change was the energy momentum tensor. And so there's an energy momentum tensor that we were able to derive from the Lagrangian after having performed a space-time shift, okay? And we were able to derive the continuity equation out of that. And so if we recall, when we did that, we came to what the change in the Lagrangian looked like. So before we came to that, we were able to show that the change in the Lagrangian was equal to, or the change in the Lagrangian, actually, you know what, I'm going to erase, this is all review here, so I'm actually going to erase the review. And we're going to talk about something new now. So if we recall that the change in the Lagrangian was upon shifting our space was equal, well, we needed to consider everything that the Lagrangian was a function of, right? It was a function of the field values themselves. It was a function of the derivatives of the field values. Okay. And it was also a function of the points on the field as well. Okay. So this was our shift. This was the overall change in the Lagrangian upon doing space-time shifting, right? In the space that we talked about, how the space-time shifting came from this right here, right? And because of that, because of the space-time shift, we had to add that extra index, right? Because, again, we weren't considering just the values themselves, we were considering the values along with the underlying coordinates. But suppose now we don't shift our coordinates and we just shift the field values, right? We don't, so I'll erase this. When we erase this, this is the change in the Lagrangian now for an internal, this is what's called an internal symmetry, right? And what we see here is that, well, we can do the exact same thing we did last time, where we replaced this with our Euler-Lagrange equation. All right, and so, my apologies, I had to take my dogs to the bathroom really quick there. So, so where were we? So we were talking about internal symmetries and how these compared with the space-time symmetries. So we can do what we did last time, right? And again, we had all these be negative last time. There really is no difference between making these negative and making these positive, but I'm gonna just make them negative for the case of consistency. And what we can do is, well, we could say, well, this again here is equal to the derivative of this is equal to the derivative of the Lagrangian with respect to the derivatives in the fields, right? So this here is actually that. And so what we get, again, is our d mu d mu phi, like this, dl, and, oh, sorry, my phone's running out of battery. Like I said, if you donate, I can get better equipment to make these better quality videos. Anyways, like that. And then we have our other term again, which is our dl d mu phi. And again, we can swap these two guys because they're really not that different. We have a change in the change in, right? So we're basically reiterating ourselves. And the reason we do this again is because we can see the pattern, right? So we have the derivative here. The derivative, it's not there, but the derivative is here, right? But then we have the derivative here, but not here. So this is the product rule, right? So if this is the product rule, this becomes negative du times dl d mu, like this, times our change in our field value, like that. Now let's contrast this with what we had last time, because I tend to like comparing and contrasting things because it really puts things in perspective for me. So this was our, this here is our internal symmetry that we've come to. Internal or not really a symmetry yet, right? We won't call it a symmetry because this is really just the change in the Lagrangian. The symmetry comes in to play when we set that equal to 0, right? So if we just set this equal to 0, then it's our internal symmetry. So this is the thing, the derivative of this object in here, the derivative of this doesn't change, right? So the derivative of this doesn't change. That means there's a symmetry. Internal symmetry. Now let's contrast that with sort of our external or our space-time symmetry. Sorry, again, that's my dog. Our space-time symmetry was 0 equals d mu. Oh, he's going to bed again. He's got a bad foot. I've heard it's growing pains. I'm not totally sure if that's a thing or not, but anyways, we had this for our space-time symmetry. So this is what our space-time symmetry looked like. So here's our, again, so our internal symmetry and our space-time symmetry. Our space-time symmetry said that this object in here, when we took the derivative of this object, that was the thing that was conserved. In our internal symmetry, this is the thing that's conserved. And again, remember, the only difference between the two is that we didn't consider this factor right here. right here. So this was for our space-time symmetry. Okay, because again, we're shifting space-time. In this case here, we're not shifting the space-time, and we come to this, which is essentially, if you look at again, if we compare this, we have this is basically this, right? But we're not taking we're not considering any shifts in. We're considering all the shifts. In other words, we're considering all the shifts in the values with respect to each direction, as opposed to doing it right here. Right? And so, what does that lead us with? Well, this here again led us to the idea that we had this thing called an energy momentum tensor, and the derivative of this energy momentum tensor equals 0. Here we don't have in this case we don't have that lower index. In fact, we don't really see any lower index in this case. Mu here became our is our lower index here, right? So we have something of a lower index, right, on our derivative, right? So we can have d mu again. But then we need this thing, right? We need something else that has just an upper index, because we don't have this nu here. We don't have this, right? And so what does that mean? Well, that means that this is equal to 0. So in one case, so for the space-time case, I don't know, my dog is whining. Again, my apologies. So we have this here, and we have this here. So this here was for the space-time case. This here was for the internal case. The internal case, again, is the case in which we're not considering shifts in our underlying space-time. Right. This is just considering shifts in the values of those space-time, in the values that are functions of those space-time of the space-time. Okay. And so what this means is that we don't really come to something like the we don't really come to something like the conservation equation, because remember, this led us to continuity equation, the continuity equation. Whereas this thing, since it doesn't have that lower index, we can't really derive the continuity equation. This really just is dt of jt plus dx mu j mu, right? So, and that equals 0. So this is this kind of is something of a continuity equation if we did it like this, right? But again, this is the difference between the two. In one case, in the internal case, we're only summing over one index. In the space-time case, we're summing over one index, but we have two indices basically in the thing that's being conserved. Okay. So you could say that this here, this is a vector, right? This here is a tensor. Those are the differences. Okay, and we haven't really gone over tensors that much, but this is a tensor, right? So we'll go over, I don't think we'll go over tensors in this, because I don't think the book goes deep into tensors, but they're very interesting objects, and I do intend on going over those, perhaps in a different video. Anyways, let's keep on going here. So if we're considering just shifts in our space, we can consider now, or in our values that depend on space, we can consider now performing this shift. A shift that might look like this, right? So this is, again, a shift if we're considering a complex scalar field, right? So if this is our field, we have a value at each point, right? Phi at x mu, but phi can be a complex number also. There's nothing stopping us from saying that this could be a complex field. So let's take into consideration now what this might look like for us, right, if we did this kind of shift. Well, we can define. We could say, look, we could take the integral over space, over our field of our j, of this thing that's being conserved, or this vector, and let's consider the 0th component of that vector. Okay, well, when we consider the 0th component of this vector, this really just means we're considering the integral of dl d0 phi times the change in phi, which is IE, right? Which is what, because we said that the change was right here. Okay, well, if we divide now, we can divide this by both sides of the equation. We can divide this IE by both sides. And we're going to call this, we're just going to define this. We're going to call it Q. And so we're going to say Q with the line over it, like that, is equal to Q IE, which is just equal to like that. So we have this here. This is a very interesting object. We could do this for the 0th component, the 1st component, and so forth. But this object here, the book actually defines as pi, which is the conjugate momentum density. Okay, so this is the conjugate momentum density. Okay, so we're defining a bunch of stuff here. Okay, the point is we don't have to do these definitions, right? We don't have to. But the point is that we are taking, this is really just taking derivatives of our Lagrangian with respect to some sort of change in our field, and we're giving special names to these. That's the point. You don't need to give special names to these, right? Because we fundamentally are really just playing with our Lagrangian. Again, my apologies for my dog. I don't know what's gotten into him. Anyways, we can then consider doing some more manipulations on this And we're going to do that right now. I figured out why my dog was crying. He wanted lunch, so I gave him lunch. Anyways, let's continue here. Where was I? I was talking about this conjugate momentum density, but fundamentally what we're actually doing here is we're just playing around with shifting our field and what derivatives in this Lagrangian with respect to different components of these fields look like, right? Because we have, this is just a derivative in the field in the zeroth component, right? So this would be the time derivative of the field. And this is just a Lagrangian. We just give that a name, right? The conjugate momentum density. And there's a reason it's called the conjugate momentum density. And again, that's going to be something that's probably going to be put in my Patreon page, just because I want to get through all this. I'm getting through names and definitions and stuff like that here. Anyways, we can consider now what a shift in we want to consider now a different kind of shift, right? So initially we did a shift that looked like this. But now we want to do a shift that looks like this. We could play around with different kind of shifts. Like nothing's really stopping us from doing this. We can be as creative as we want. E to the I, like this. And this is what's called a phase shift, right? Because when you have e to the I of anything, well, that's an oscillatory function. You have phases in these functions. What this does is it allows us, we can Taylor expand this, and we can approximate we can Taylor expand this, and this actually becomes a minus sign if you understand Taylor expansion. And we get phi here. Similarly, we can do a phase shift that looks like this, where that's a positive, right? And we set that equal, well, that's just going to be plus I e plus any negative terms or any positive terms following. Right. Well, if we truncate this, this is approximately equal to, and I'll move this over, move all these over just to give myself some space here. This is approximately equal to phi minus I e phi, and the phi plus I e phi. But what we want to do here is we want to we're going to call this the conjugate field, because again, we're looking at a complex field. So when we phase shift our field in one direction, we're also saying we're phase shifting the complex field sort of in the opposite direction. And so these become the complex, or not the complex, the conjugate, right? These are the complex conjugates. That's what these daggers mean in the subscripts of the fields. So again, what I'm doing is I'm really just playing around with different kinds of shifts, right? You can do this as much as you want. You could say, well, you can come up with your own arbitrary shift. And you can play around with it with complex and not complex fields. You can play around with all this kind of stuff. The point is that what this fundamentally is going to come down to is looking at how these shifts correspond to some sort of change in your Lagrangian. So we can consider now the change in the shift of the field as being negative IE phi, because that one's right here. And the shift in our complex part, or our complex conjugate, is IE by complex conjugated, like that. Right? And we can contrast this with what we said down here. This here, there was nothing right here, right? But when we phase shift, we do get our field value in our shift, right? So this is a phase shift, as opposed to what we did earlier right here. This was not a phase shift, not a phase shift. Phase shift. Again, this video might be a little bit longer than 30 minutes, but after this video, we're going to jump into chapter 5, which is all right. My apologies. My dog started barking at the mailman. Again, when you guys contribute to my Patreon page, I'll be able to lock myself in a room and make myself an office where things will be much more smoother. And you won't hear the pitter patter of my dogs or anything like that walking in the background. But anyways, we were talking about phase shifts, and we were talking about how they were different, or sort of fundamentally different from these non-phase shifts, which were down here. And this all hinges on the idea that our field that we're shifting is complex. It has complex values to it. And in this case, it's a scalar field. It doesn't necessarily have to be a scalar field. Right? We might want to consider complex vector fields or complex spinors. So spinors are naturally complex. But anyways, let's get back into this. I don't want to belabor this for too much because I think we are past the 30-minute mark. But anyway, so we can talk about how so we talked about these are the phase shifts. And what we can do now is that since these are the shifts, we can apply these to here, right? So here, this is where our shift was, because this was the change in our field value. So we can actually apply those to our integrals. And I'm just actually going to say, well, we had an integral. An integral d3x like this, our change in our Lagrangian like this, and then we have negative IE phi like that. And what we're going to call this is we're going to call this J, because we did that over here. This here, right? So this right here was J, right? So we have J, right? But we have two different types of them, right? Because we have d3x dl d mu phi, i.e. phi dagger, like that. And the book calls this mu 1 and mu 2, where 1 and 2 correspond to if it's the complex conjugated version or not, right? And so we could say that J mu is equal to J mu 1 plus J mu 2, okay? And when we do that, we're really just adding these together. We're adding this to this, just like we're doing right here. And what we end up with is our Q. Remember we said Q was this, our Q was this right here. And I keep on going back and forth here, but this is our Q. Just remember what that looks like. We have it showing up here. We just have this extra phi, right? So what ends up happening is we get that Q equals the integral of that over our space, is equal to, we have that minus sign, which is right here, which is where that came from. And we have dl d mu phi e phi plus dl d mu phi dagger e I phi dagger. Okay? And so that means Q, this is just equal to Q. This was a definition. And I'm just going to copy this because I don't want to write it out all again. Paste that. And that is equal to that. And we're just not going to have these guys in here. And what we have now is our invariant quantity, right? This is the invariant quantity that happens under a phase shift for a complex scalar field. Right, so we phase shift the values in our field, and when we do that, the thing that's invariant, again, is what I've just underlined here in red. We're not going to name this anything. We don't have to name it anything. The point is that we have these arguments that show up in these integrals. And these are the things that end up being invariant under these types of transformations, right? So under these types of shifts, again, we got this, and under this type of shift, we got this, right? We didn't necessarily have to put a 0 here, but putting a 0 here applies to what's called a conjugate momentum density. When you don't put a 0 there, that's just more general, right? So again, I've gone over a little bit. I've gone over my time a little bit, but this is the end of chapter 4. And what I think I might want to do is I might want to summarize chapter 4. And if you want to take a look at that summary and all the equations that correspond to the different kinds of shifts, then you can go into my Patreon page again. And again, on my Patreon page, I'll have summaries, I'll have derivations of things that I don't go over here, and all that good stuff. But anyways, without further ado, let's get into chapter 5 now. So I'll see you guys in the next one.